Hi students, now I'm going to teach a topic on linearity, sensitivity and loading effect. So what is a linearity? Output follows input. Output follows input. Output follows input with a linear relation. Okay now? The next what is here you had a straight line characteristics. That is what in your circuits you might be saying straight line characteristics, linear elements and all like RLC. So it is of a linear scale. It is also called as uniform divisions. Then next, so non-linear scale will have non-uniform divisions. Here it is very cramped. Here it is cramped means their divisions are very near, and linear means they are uniformly distributed. Expanded means non-uniformly they are very far. Okay now next have a question on which of the non-linear scale is preferred in order to measure 7 volts, in order to measure 17 volts. So I can give, see, if in the question they asked linear scale means your answer is 20 volts. The question, if it is of linear scale means it is of a 20 volt scale, but I gave you non-linear scale. Once you distribute 0 to 30, so 17 volts will come in a linear scale. So your answer is of a linear scale. So then next, so I can give you one note. Choose a pointer in such a way that it enters into linear portion. It enters into linear portion so that it may not lose accuracy. Okay, now very important point. The next, what is sensitivity? What is sensitivity? Figure of merit and a scale factor. So what it is defined as a ratio of a change in input, change in output to change in input. So I can give a formula as S is equal to change in output by change in input, change in input so I can give as S is equal to what input output I can change in deflection angle by change in the current. Okay now then next I can give, so I is equal to V by R now. I is equal to V by R. So sensitivity is equal to R by V. Sensitivity is equal to R by V. So what is R? Resistance of voltmeter. This is resistance of voltmeter. And this is what V is of a range of a voltmeter. And this is sensitivity. And this is sensitivity. Okay now. So from this I can give what earlier we had a relation. From this relation, from this equation, what S is equal to del theta by del I. So from there I can give S is equal to 1 by IFSD. Okay, now this is also one of the very important formula. Then next, so what are the units for sensitivity I can give? Sensitivity is equal to ohm per volt units. Sensitivity units are ohm per volt. So then next I can give for all electrical instruments, responsible quantity is current. For all electronic instruments, responsible quantity is voltage, because electrical instruments respond for the current entering into it, and for all electronics the potential difference that exists between them. So listen here for a while. In your PMMC MI dynamometer type wattmeter, your TD is directly proportional to I. Whereas whenever you go for digital voltmeter and CRO, their voltage will play a major role. So we always prefer high sensitive instrument. Sensitivity indicates a loading effect. Very important objective. Sensitivity indicates a loading effect. Earlier it was asked in IAS. So then next, how sensitivity is placed in. So sensitivity in a linear scale. Okay, now how sensitivity is placed in a linear scale. So directly sensitivity I can give here as, so change in the slope is constant now. So if I treat it as an input I, and this I can treat it as a output theta. So what is the change? So for all I can give, for all linear scales, sensitivity is always constant. Sensitivity is always constant. And then next, for linear scale instrument, so S is equal to tan theta 1 is equal to 1, since theta is equal to 45 degrees. So the next, sensitivity in nonlinear scale. How sensitivity is in a nonlinear scale? So I can give, so as this is a linear portion, S equal to 1, S greater than 1, so S less than 1. Then next, what is loading effect? A very important topic. A very important topic. So whenever electrical instruments connected in circuits for measurement purpose, then circuit conditions are modified, consume some minimum current for its working. Then indicates a value, less than true value, So what I can give an example for this is as, So I will take here 100 volts. So I had a resistance. It's of a 25 ohms. So I gives rise to what I is equal to 100 by is equal to 4 amperes. So once the same, but this particular, in order to know that 4 amperes is passing, we need one ammeter. We need one ammeter. So what 100 volts? I should take I, and this particular 25 ohms. So I should know the ammeter, and this ammeter Rin will have 1 ohms. Therefore, I is equal to 100 by 25 plus 1 is equal to 3.9 amps. So what is percentage loading effect? So I can treat this as a true value, can treat this as a measured value. So then next, percentage loading effect. Percentage loading effect is equal to measured value minus true value by true value into 100. So I can give this as 3.9 minus 4 by 4 into 100. So this gives rise to minus 2.5 percentage. Okay, now how this is in case of say shunt connected meters, and so loading effect for all shunt connected meters means voltmeters. Okay, now so what, let's have a ideal case first of all. I will have one battery E naught, one R naught, so this is my R naught. You will have E naught, so you will have here A, B. So I can treat it as a true value. So what I can name it as this is a cell or a battery. Cell or a battery. And this case study, first of all, this is without voltmeter. This A, this is without meter. This is without meter. So without meter, I can name it as this is ideal value E naught. This is because the source, whatever the source voltage E naught is equal to output voltage. But let's come for after connecting meter. Once I connect meter, this is your E naught. This is for R naught. After connecting meter, This is what measured value. I'm going to connect one voltmeter, load current IL, RV equal to RL. This is B case. After connecting meter, so EL is equal to what? I am applying voltage division rule, not more than that. I am applying voltage division rule. I'm applying voltage division rule. EL is equal to E naught into RL by RL plus R naught. So what I said, I want voltage across here. So what total voltage into the same resistance RL by RL plus R naught, not more than this. So once I can go by EL is equal to, so divide both by RL, divide and multiply by R divide. So dividing and numerator and denominator by RL, what we will get? EL is equal to 1 by 1 plus R naught by RL into E naught. So I can give a percentage loading error. We can give percentage loading error EL minus E naught by E naught into 100. So simple it is of what is the meaning of it is measured value minus true value by true value into 100. So I can give always measured value EL approximately equal to E naught when RL greater than R naught. Okay, now the next a voltmeter should have a voltmeter should have high resistance. A voltmeter should have high resistance based loading effect. A voltmeter should have high resistance based on loading effect. So I can give sensitivity is equal to ohm per volt, is equal to R by V. When resistance is high, sensitivity is high. So implies accuracy is high, loading error is less. Loading error is less. So then next, what is EL? EL gives rise to voltmeter reading. EL gives rise to voltmeter reading. And E naught gives rise to circuit voltage. Naught gives rise to circuit voltage 80. True value. R naught gives rise to circuit resistance. R naught gives rise to circuit resistance. RL gives rise to voltmeter resistance. Then next step, the voltmeter resistance is more, if the voltmeter resistance is more than the circuit resistance, the voltmeter resistance is more than the circuit resistance, then loading effect decreases. Then loading effect decreases. Then next, design voltmeters. Design voltmeters with high resistance. Design voltmeter with high resistance to reduce loading effect. To reduce loading effect. Decrease voltmeter to reduce loading effect. Then next, to obtain 99% of loading, to obtain 99% of loading accuracy, loading accuracy by the voltmeter, accuracy by the voltmeter, the voltmeter resistance, the voltmeter resistance should be, the voltmeter resistance should be 100 times of circuit resistance. 100 times of circuit resistance. So this gives rise to EL is equal to 99% of E naught. So EL by E naught is equal to 0.99. So 0.99 is equal to 1 by 1 plus R naught by RL. So RL is equal to 99 R naught. So RL is equal to 100 R naught. RL equal to 100 R naught. So I can finally give as so next is our case study is of series connected meters. So series connected meters. So loading effect for all series connected meters. Loading effect for all series connected meters. So the next first thing is without ammeter. First thing is without ammeter. E naught R naught. So I can take this as I naught is equal to E naught by R naught. Since it is of a since there is no meter, since there is no meter, I can treat it as a true value. Now let's come with meter. So let's come with ammeter. So actually this becomes of E naught R naught IL IL is equal to E naught by RL plus R naught. RL, this is what your so denominator part EL by RL plus R naught. RA is equal to RL. So IL is equal to E naught by R naught plus RL. So then next I can give IL by I naught is equal to R naught by R naught plus RL is equal to 1 by 1 plus RL by R naught. This gives rise to IL is equal to 1 by 1 plus RL by R naught into I naught. So then next I naught is what I naught is circuit current. So this is a water true value, and RL is equal to ammeter resistance. So for ammeter resistance, and IL is of IL is of indicated value. IL is of indicated value. So this gives of a measured value. So then next, if RL less than R naught, means your ammeter resistance less than load resistance, then IL less than I naught. So then next, to reduce loading effect, or to improve accuracy, to reduce loading effect or to improve accuracy in indication, ammeter resistance must be less than circuit resistance. So this gives rise to IL is equal to 99% of I naught, then RA is equal to 1 by 100 R naught. Therefore, RA is equal to 0.05 R naught. So this is what your loading effect for series connected meters. Loading effect for all series connected meters. Thanking you.